All right, welcome everyone. Today we're going to keep talking about series, and specifically we're going to look at the definition for what it means when a series is convergent. And here it is. Here's our definition. So let's read through it. It says a series sigma an is convergent if our sequence of partial sums, so that's what S sub n is, it's our sequence of partial sums, if that sequence converges to a number S. So that number S it's special, and we call it the actual sum of our series. All right, so how are we writing this out? Well, sigma a sub n, that's just our original series. And we're saying this is equal to the limit, and what we're seeing right here, these are just different ways of writing what our partial sum is. So each of these represents the nth partial sum. So S sub n is just kind of like the shorthand notation. That's what we're calling this brand new sequence of partial sums, just S sub n. And then this is how we're actually calculating it. This is where if we remember back, this is where we're adding up the first n terms of our original sequence. So let's kind of remember, when we talk about series, there's a few different things we're talking about. So we're talking about our original sequence, a sub n. And essentially, these are the terms that we're trying to add together. So we know that a series, what is it? We're taking an infinite list and we're trying to essentially add up all the terms. So this is the list of terms. This is our sequence of terms that we're trying to add all together. Then we have our sequence S sub n. This is our sequence of partial sums. So what we're doing here with S sub n, if we remember, we're taking the first n terms and adding them together. Then to get the next term in this sequence, we take the n plus 1 terms and add all those together. So we're adding up the first n terms from our original sequence. So like S1 was A1, S2 was A1 plus A2, S3, A1 plus A2 plus A3. So S sub n, we're kind of getting in some way from our original sequence. We're just adding up some of the terms, the first few terms from this original sequence A sub n. And then what we're also talking about here is our series. And we call this sigma a sub n. So there's kind of a few bits of notation here. So it's going to be helpful to try to keep these three different things kind of clear. So we have our original sequence a sub n, we have our sequence of partial sums S sub n, and then we have our series sigma a sub n. And this is where we're trying to add all of the terms in a sub n together. And really how we discuss whether we can actually do that, can we add up an infinite number of terms? Sometimes yes, sometimes no. But how we actually define this is with our sequence of partial sums. And that's what we're seeing here. We're seeing how we actually, if we can add up all those terms together, how we actually do it. So adding up all these terms of a sub n, how are we doing it? Well, we're adding up the first n terms and then doing the limit as n goes to infinity. So that's what we're seeing here with this definition. We're seeing our partial sum here. So we're adding up a1, a2, up through an, and then we're doing the limit of that as n goes to infinity. And if we get a number out, well then the sequence of partial sums converges, and then that's actually what the sum of this series is. So sometimes we also write, if we want to write this out, we can also express this as a1 plus a2 plus a3 plus ... up through an, and then we keep going. So our original series, another way to think of it, again, is just we're adding up all the terms of our original sequence an. So we're adding them up. And the dots just mean it keeps going. We keep adding. And that sum, that infinite series there, is equal to S for a convergent series. All right, so there's a little bit of kind of subtlety here, a little bit of work in showing that a series is convergent. And it definitely can fall apart. We know when we talk about limits of sequences, there's sequences out there that the limit does not exist. So what happens if we're calculating this limit of partial sums and we see that the limit does not exist? Well, then we say that our series sigma a sub n is divergent. So that again happens when our sequence of partial sums diverges. Might get really big. It might just kind of bouncing back and forth between a few different values. But in any case, if this sequence of partial sums diverges for whatever reason, we say our series diverges as well. All right. Let's look at an example. Example 3. This is a fun one. This one is probably a little too much fun. All right, so we're going to show that this series is convergent, and we're going to actually find its sum. So what is our series here? It's sigma 1 over n times n plus 1, and we're adding up the terms starting with n equals 1 going to infinity. So this is our series here that we're investigating. And how we're going to get started with this is, well, if we look at just this nth general term here, 1 over n times n plus 1, it's a fraction, and there's two distinct linear terms in the denominator, so there's actually a partial fraction decomposition. So we get a nice review here of partial fractions, not to be confused with partial sums. So just different ideas. But we can use partial fractions on this expression 1 over n times n plus 1. And I'll leave it for you to kind of work out the details. But if you did work out the details, you would see that we could rewrite this expression as 1 over n minus 1 over n plus 1. All right. So a little bit of work there that you might want to try. Good practice doing a little partial fraction decomposition there, but we'll take this as something that we can work with. All right, so when we want to investigate the convergence of a series, let's go back to our definition for a second. What do? We need to evaluate the limit of our sequence of partial sums. So we need to find our sequence of partial sums. So let's start writing out the first few terms of our sequence of partial sums. And this is where the fun happens. We're going to start writing out the first few terms for our sequence of partial sums. So let's start with S1. And this is just where we take the first term of our sequence. So here's what's in the parentheses here. This is our formula for a sub n. So we have our sequence, and then the series is what we're trying to do. We're trying to add up all those terms in our sequence. So we have our original sequence here, and then we have our series, which is what we're trying to do. We're trying to add everything together. All right, so to find S1, we just take the first term in this sequence, and we know we're starting with n equals 1. So what do we get? I'm going to leave a little space here because we're going to be doing other partial sums. So A1, we're just plugging 1 into this formula, and we get 1 over 1 minus 1 over 2. Okay. Now let's find S sub 2. And S sub 2 is where we take the first two terms of our sequence of original sequence. So we take A1, we take A2, we add them together. So let's do it. So A1 we already know. It's right up here. Put a nice set of parentheses around that. And then A2, now we're going to plug 2 into this formula. So we're going to get 1 over 2 minus 1 over 3. And we're just adding those results together. So that's our second partial sum. Don't worry, we're gonna come back and simplify these in a second. Now let's look at S sub 3, and this is where we take the first three terms. So A1 plus A2 plus A3, taking the first three terms of our original sequence, adding them together. So let's do it. And we already know what A1 is and A2 is, so let's just rewrite those. And now what is A3? Well, find A3, we just plug n equals 3 into this formula. So we get 1 over 3 minus 1 over 4. All right, so there's S sub 3. And brace yourself. We're going to do some simplifying in a few minutes here. All right, let's do one more. So it helps when you're ultimately what we're trying to do is we're trying to figure out a formula for the general term. So that's what we're ultimately trying to do here is we're trying to find a formula for the general term S sub n. And so to do that, it helps to write out the first few terms of that sequence. That's what we're doing here. We're writing out the first few terms of our sequence of partial sums. And hopefully we'll be able to figure out the pattern. So probably not quite seeing it yet, but once we simplify this, it should hopefully be, we should be able to spot it. All right, so let's do one more. Let's find S sub 4, our fourth partial sum. And so we just take the first four terms of our original sequence A, and we're just adding those first four terms together. So A1 plus A2 plus A3 plus A4. And we actually know what all of this is. So this was A1 plus A2 plus A3. Now we're just adding one more into the mix. So A4, how do we find A4? Well, we're plugging n equals 4 into our formula here. So 1 over 4 minus 1 over 5. All right, so let's see how everything simplifies here. So let's start with our first term here. 1 over 1 simplifies to just 1. So let's just leave it as 1 minus 1 half. All right, now let's go to our second term, S2. And when we look at this, notice that we have this minus 1 half and this plus 1 half. So those are going to cancel. And then we're left with just the 1 and then the minus 1/3. So notice everything in the middle here canceled, and we're just left with our first term and our last term there. Now let's look at S3, and we're going to see even more canceling. So we start off with 1, but then we have a minus 1 half and a plus 1 half, so those are going to cancel. Then we have a minus 1/3 and a plus 1/3, so those are going to cancel. And this whole thing just kind of shrinks down. And it shrinks down to just 1 minus 1 over 4. And what about this last one? Well, we're still getting that same kind of behavior. The minus 1 half and the plus 1 half are canceling. The minus 1/3 and the plus 1/3 are still canceling. And then we have a minus 1/4 and a plus 1/4 that still cancel. And all we're left with here is the first one, the 1, and then this minus 5 at the end. And so we want to identify the pattern. And I mean, if you wanted to have a lot of fun, you could probably even do S5. You get a whole bunch of canceling there. It's just a lot of fun to do this. And, when we do this canceling, you can kind of see in each step, each new partial sum, it kind of collapses down. And for that reason, we sometimes call this a telescoping series. So there's other ones like this. They all kind of, a lot of them involve like this partial fraction decomposition where you get two fractions, one of them's positive, one of them's negative, and you kind of get this canceling effect. It's just kind of fun to work out because it simplifies down quite a bit, and you can probably identify the pattern now. So for when n is equal to 1, for our first term, we're trying to identify the pattern, and we know that each of these has this 1 in front. So we can say that S sub n is going to have that 1 in front, and then we're subtracting. So each of these has a subtraction there. Each of these also has this fraction, and the numerator is also 1. So we just need to figure out, well, what is the denominator going to be here as we go along? So when n is 1, for our first term here, S sub 1, the value, the value in our denominator is 2. Okay, so n equals 1, we have a 2. When n is equal to 2, what is the value in our denominator? It's 3. So we might start seeing it. Let's look at one more. When n is 3, the value in the denominator is 4. So what we're seeing here in each of these is when we take our n value, we end up with 1 more here in the denominator. So we end up with n plus 1. And you might just look at n equals 4 just to confirm it. So once you come up with your formula here, it's kind of a guess, kind of guessing here. And you just want to see if it actually agrees with what we have for S4. So when n is 4, what do we get? We're going to get a 5 down here, and that's exactly what we see. So it actually does kind of match up. All right, so we're able to actually find the general term of our sequence of partial sums. And as we're going to see in later lessons, being able to do this is exceedingly rare. In almost all of the series we're going to look at, except for this one and maybe there's a couple others we might take a look at, but almost every single other series we're going to look at, we're not able to do this. So being able to find these general terms of our sequence of partial sums is usually very difficult. So why this one is so special is because we're actually able to do it. And because we're able to find this nice general term here, it's nice and simplified, it's a nice little formula, we're actually going to be able to do the limit of it. So that's what we're going to do in the last part here. So we know our series. And it's equal to the limit of our sequence of partial sums. And it's the limit as n goes to infinity. Now it's playing tricks on me. All right, we'll go with green. Guess it didn't like blue. All right, so what we're seeing here, we're doing the limit. We're applying the definition of a series, a convergent series, in that we're investigating whether we can actually do this. We can add up all these terms together. So we're doing the limit, and what we have here is our sequence of partial sums. And so we have this nice little formula for our sequence of partial sums, and we're doing the limit as n goes to infinity. So this is S sub n. All right, so this is something we can just do. So what is it? Well, the limit of 1 is 1. The limit of this fraction is 0. So we end up with 1. And, why does this fraction go to 0? It's one of our c over infinity forms. Just to provide a little justification. So this one fraction here, it's one of our c over infinity forms, so we know that it goes to 0, so we end up with 1 minus 0, which is 1. All right, so we have all of we've actually calculated the limit of our sequence of partial sums. We actually get a number, so what this says is that our series, sigma from n equals 1 to infinity, says it's convergent, and the sum is equal to 1. So that's what this is saying. The fact that we calculated this limit and we got a numerical value told us two things. Our original series is both convergent, and that's actually what our sum is. It's equal to 1. So if we were to add up all those terms, what we're getting is we're getting 1. That's the sum. So pretty remarkable. And as it turns out, there's going to be very few series that we look at where we actually can say this much. So for the most part, all we're going to be able to do, we're going to be developing a bunch of different tests that allow us to say whether a series is convergent or divergent, but we're not going to be able to say exactly what its sum is. So this is one of our special series here. And we'll be looking at a couple more of those. All right, so let's just talk about some of the algebraic properties for convergent series. And if we have two series, sigma a sub n and sigma b sub n, we know they're convergent, then they behave very nicely with addition, subtraction, and constant multiplication. So what this is saying is we can essentially add two convergent series together and the result is convergent. We can subtract two convergent series. The result is a new convergent series. Or we can take a convergent series, multiply it by a constant, essentially bring the constant inside, or if we want to bring the constant outside, and the result is still convergent. So you can kind of think of these two ways. You can either bring the constant outside of the big addition sign, kind of factor out the constant. You can split up the addition. But really what we're doing here is just looking at different ways of combining convergent series. And notice though, so a little bit of a warning, there's no rules here for multiplication or division. So this only works for constant multiplication, addition, and subtraction. So no rules for multiplication and division. So just, you might find it tempting. It's like, oh, let's just take two series and multiply them together. That's not what these rules are saying. Only working for addition, subtraction, and constant multiplication. So just a little warning there. All right, let's see how we use these. Let's look at example 4. And this will be the last one. So we're going to determine the sum of the series sigma 5 over 3 to the n minus 1 over 2 to the n, then goes from 1 to infinity. So here we have a series, and we're investigating whether it's convergent. And if it is convergent, we want to find the sum. But we know that we're going to assume at this point that we know these two statements. We're actually going to see these in the next lesson, so we're actually going to prove these later on. But for right now, we're just going to assume that we know this. So we know that the series of 1 over 3 to the n is equal to 1/2, and we know that the series sigma 1 over 2 to the n is equal to 1. So what this is saying is that each of these is convergent. So each of these is convergent, which means that we can do some arithmetic with them. We can add convergent series together. we can subtract them, we could take one of these and multiply it by a constant, and we would still have a convergent series. And that's what we're seeing right here. So the first thing we see is the subtraction. So by that one rule that we just saw, we could split this up into two separate series. So we're going to have the series sigma 5 over 3 to the n minus the series sigma 1 over 2 to the n. So we're just splitting up where we saw subtraction. And that 5 there is a constant multiple. There's no n attached. So that's just a constant multiple. There's no n attached. So what we know with constant multiples, if we go to back to our list of properties here, we could take that constant multiple, that's c, and essentially we can factor it out of the addition. We can bring it out in front of our series and just have it in front. That's what we're going to do. And while we're here, we also have the subtraction property that we used. So we had two terms being subtracted. We just broke the series up. All right. So let's get this 5 out of there. So we're going to put the 5 in front. And now we actually know, what do we know? We know what the value for this series is. We know what the sum is. And we know what the sum of this series is. So we just fill those results in. So we know this one is 1/2. This one is 1. So just fill those in. So we get 5 times 1/2 minus 1. And doing the arithmetic there, what do we get? 5 halves minus 2 over 2. So we get 3 halves. And so what this is saying is this value here is the sum of our new series. So we know it's convergent, and we actually know what the sum is. So the sum of this series here, if we're following our thread, is 3 over 2. And we got that because we knew this series was convergent, and we knew its sum, and we knew this series was convergent, and we happened to know its sum. All right, so we're going to stop there for today. Next time, we're going to actually investigate these types of series here. So these ones are also special, and as you can see, we're going to be able to figure out their sum. So we're going to see that next time, called a geometric series. So we'll see you then. Bye-bye.